All right, so today, as we said, we switch gear and go into the concept of a new language that are closer to system, right? But before we begin, let me do a quick announcement. Someone doesn't turn off their microphone. Can you? There's a lot of echo. I'm not sure. Is that? Wait, is this? It's off. Okay. So a quick announcement, assignment 1 is posted. I feel like somebody is almost done. For some reason, based on some of the Discord chat that I got like yesterday. A second bullet point, there's a small chance I might be late a little bit on the class on February 2nd. I'll let you know a little bit more detail on this. Basically, I'm buying a house and the salesman told me it was like from AP and I'm like, I can only do this, like I can only transfer the money either on Tuesday or Thursday. And I told him like, well, I have class on Tuesday and Thursday. Like, can you be a little bit more flexible? You are literally taking so much money from me, right? And he was like, nope. I'm like, well, so I'll start that as early as the government office open in the day. And I'm basically trying to do all the paperwork at a time so that when we got there, it should be only 1 or 2 hours, which means that by 11, I should be done. There's like a slim chance that I might not be able to make it like straight right at noon, right? But I'll try my best. If not, I think one thing I am planning to do might be just like do a pre-recording of the class, right? So if somehow I disappear on Tuesday, February 2nd, when I show up around like 12:30, you can choose to like check out those and then I'll basically go through the material, right? And then do the usual, like go through Q&A and everything. And if we do have to do like a makeup class, I'll make sure everything is covered, right? I'll make sure every single baht that you've spent on tuition, it doesn't get wasted by me buying a house. So that's it. And past lecture video all available now. And thank you. But I mean, it is a lot of money too. It's like, I'm not sure. At the end of the day, it's like you're buying thing. It's just that thing costs so much money. It's like my entire saving. I feel so bad for you guys when you have to like actually get a job and start looking for housing and because everything is skyrocket, right? The price inflate like crazy. I was surprised when I was away for 10 years in the United States. I'm like, I thought this much I should be able to afford a house. No, anymore, not anymore. Not everything is so far away. Regardless of that, lecture video will be is available. And today we will dig deeper into trying to understand this thing called computer, right? We've been using them for a while, and a lot of the news media and whatever is trying to like make this fear or like trying to like build this fear of like we don't know what AI and robotics would bring and things like that. And one thing to kind of like protect you against those kind of fear is to know how they work, right? Knowing how AI and machine learning works would be good. Knowing how some of the application of that can be a powerful thing and good thing. And knowing how they are like not perfect, right? They are still like a lot of work required for them to be good. And knowing what's the limitation of computer, knowing how computer works, all like contribute to better being a better engineer, computer scientist and computer engineering. So this while I understand you're in like computer science, right? Department. Today we'll touch like that boundary between computer science and computer engineering. I always make a joke, which is true, that what I do, computer architecture just sit right in the middle between computer science and computer engineering. People in my research group back in when I was at CMU, we both come from both schools, computer science and computer engineering, because we literally in that at that boundary. So what should you at least aware about computer? Logically, like you have logic gates. Logic gates are those circuitry that designed to perform computation. When you say plus, you want to add something, right? Uh, when you want to add something, you basically driving electrons from one place to another from one data representation A plus B into the actual summation of the value of A plus B somehow, right? That's also control signal. What do I mean by control signal? If I have just logic gates, the unit that's capable of doing the add, capable of doing the subtract, I need to be able to control them. Like do that add, followed by do that subtract, followed by another add, right? So that's the control signal. And then the obvious part, you have the storage element. These days you're looking at, sorry, let me turn on the AC. It's noon and it's kind of hot in my room right now. The storage element is essentially the backbone of where you can store everything, right? And if you look at modern system, there's the actual hard drive, right? Where you like put all the files in, and there's the memory, and there's a big distinction between the two. And I'm gonna kind of briefly touch it today, but then we'll kind of cover a lot of them toward the end of the third module when we talk about caching and virtual memory, and then we go like way into detail. For those of you who want to do computer architecture or take that class, right? I will go into more details on how things work. But also, if you kind of like put in your scientist hat and like, or I guess physicist hat, right? Everything is just tons of electrons, tons of bits. Why do I care about bits? Why do I care about binary? If you think about it, right? If you want to represent your data using electricity, right? You can have this thing called voltage, right? That can have, it can be zero, it can be high value, right? So I guess computer engineer, we kind of like came up with an idea of like, okay, back in the day, we are not really good at isolating high and low voltage. So let's just put in, say, 5 volts for your power supply. And if you read 5, it means 1. If you read 0, means 0, basic 0. That means you can represent binary, right? Using high and low voltage. You basically have something like this. If your circuit, if you read the voltage and you see something like this is 5 volts and this is 0 volts, right? And you make this cut off, the clear cut off between the two. You can say, hey, this is a value 1, this is a value 0. So you can send data. You can send data through the wires, right? It means you can read data. You can transfer data from one place to another, just sending electrons, or just stop sending electrons, right? So that's kind of like the really basic of like how bits work and why do we care about binary? Because everything in your computer can be converted to binary. If you look at ASCII symbol, right, the letters that we see, A, B, C, D, E, F, G, they can be converted to binary number. It means that computer can now understand human language to some extent, right, as long as we can program them. So physically, if you want to transfer data over, there's a transistor. What are transistor? Transistor is kind of like components that we use to store these electrons and used to drive electron from one place to another, but we need to drive it to wires, actual electrical wires, the copper wires that you see inside your computer. If you open it up, you look at the motherboard, you see this copper looking things everywhere, right? Those are wires, literally wires that connect like, so that electrons can move from one place to another. You have resistor. Resistor is there to put in some control, making sure you can control that, hey, don't go over 5 volts, otherwise I will actually burn this thing. I actually by accident burned my, like not my, but like when I was taking embedded system class back in CMU, my fingers are pretty not nimble at all, right? So I need to solder like resistor into the board. And by accident, I kind of like connect the two wires that I'm not supposed to, and it short circuit. I can smell the burning of the circuitry inside, and the whole board broke. It's a cheap board, so that I can play around with it, right? And the TA was like, how can you do that? I'm like, yeah, I'm not good at soldering thing. And I tell my groupmates like, from this point on, can you please like help me with this? Yeah, I should not be like surgeons as well. Like I'll probably kill people. And then the capacitor, what is a capacitor? It stores things, right? It actually stores electrons. So you can store the value. You use capacitor and transistor to store and read write value. So the combination of these things allows computer as a whole, right? As a bunch of these things, create a bunch of bits that somehow mean something. Somehow magically you write a program, it runs, things appear on the screen, right? When you play Dota 2, when you play Cyberpunk, which I hope you haven't bought yet, it seems like a disappointment, or Witcher 3 or something like that, right? Nothing, it's not magic. Everything is like backed by proper science, and at the core of this, just a bunch of electrons that has high and low voltage. Literally, it's like make sure you are aware that at the end of the day, it's just high and low voltage everywhere. So computer nowadays is really, really diverse, right? You can have things like Raspberry Pi. Everything looks like a normal computer. It actually is a normal computer that's on chip, right? It has a bunch of ports. You can actually like connect this thing to a monitor and install Linux, install the NES emulator, and you can play games. Like you can actually emulate like a Super Famicom. I think it might these days it might be good enough to like emulate Nintendo V. You can like do crazy things with just this like small form factor, right? You can have this thing is a GPU, right? It's an NVIDIA card. Most people buy it for basically playing games that include myself. A lot of people also buy it to like mine Bitcoin back in the day. These days you don't buy GPU to mine Bitcoin, you lose money because actually you drain more too much electricity that you don't get anything out of it. And to be honest, I kind of hate Bitcoin as a technology in the first place because I'm not sure I should go sidetrack, but like I hate Bitcoin with a passion because it's not like designed to be what it is right now. It's not like a tool for people to like, gain money. It's just a mean to transfer goods, right? It's designed to be actual money. You don't trade money to try to gain profit. It's so different. And also, if you know computer systems and you know how Bitcoin works in terms of the technical background of it, it sucks. It's so inefficient that I think right now you can probably power a small country because of these people mining things, right? It's so like inefficient that it creates like greenhouse gases. It's bad for climate change, and people just want to make money and not they're not aware of it and how much power these inefficient things consume because they don't trust the government. I can understand why you don't trust the government, but if you know the technical background that creates Bitcoin, it doesn't make sense to have this as a long-term solution because it's not power efficient at all. At all. So I hate that with a passion. That's the reason why I hate that with a passion. I feel like climate change is a big problem for us, for you guys, because you will run head on into that problem for your generation for sure, right? You should be scared of that. I should be scared of it. So I should not promote technology that would kill us. So for going super off topic, I kind of want to like on here. There's also this thing is a big server, right? This is a picture from Lawrence Livermore National Lab. Where's this place? It's in the United States. It's one of the big national labs. It's kind of like NECTEC, right? The US has the same thing as NECTEC. And to be honest, if you've been looking at what people at the national lab is doing, they're doing a lot of cool things, right? How many of you here heard about Thai SC? It's the new supercomputing center by NECTEC, and actually the people behind it are like a group of really cool people. They are people who did like high performance computing. They came back from like basically they got like this scholarship contract like I do. We have to be tied to the Thai government for a long time, right? But we came back here and we want to make changes to make things better, right? And one impact that they're trying to make is that they get together, hey, we need a proper supercomputing center for people, for researcher to use, right? So there's Thai SC, Thai Supercomputing Center, that actually now have a cluster machine where researcher can send in proposals and they'll give a really deep discount. It's a lot cheaper than Amazon Cloud. And you can run things on them, right? So you can run experiment that hopefully would improve the scientific knowledge. And I'm talking about proper science, right? There's so many like bad scientific proposal by Thai professors, and I don't want to talk about those. I want to talk about proper science. So we have national lab. It actually looks kind of like this thing. Is these are blade machine? These are like a contain, like a big box of like I guess enclosure. Inside you see this blade. Each blade is a big computer, like a basically big ass computer inside there. It's a CPU with multiple cores. You look at like 48 cores, 60 cores, right? A lot of memory, a lot of drive, right? So these things are our SysQ server is like a miniature version of this, like super miniature version of this. But the way you use it, the way you use SysQ is the same as what you do here. It's the same way, right? You go log in using SSH. Linux is basically the backbone of that. Usually it's instead of Ubuntu, they use CentOS or Fedora because they are more stable. It's less likely that someone can come in and destroy things. And you can use it similar to how you use SysQ. Apple iPhone, right? Such a powerful machine. And whenever, so I'm gonna tell every single one of my students every time on all the class in the system, skill class is that the iPhone that you own these days are super powerful. Apple actually has a really good architecture team. Like they actually hires a lot of great people behind the scene, and they came up with a chip that's like you can use that chip to power a laptop and they'll run fine. You won't notice the difference. They'll run fine for multiple years. And actually, that's actually why one of the reasons why when you change an iPhone, it's because of like you want new features. It's not never because of like it's slow. Most of the time because you want new things like better camera, better I don't know, like you hate yourself and want an iPhone without the headphone jack, or or actually like have a better screen, better monitor, right? But the performance is rarely an issue on iPhone because it's really powerful. And this happened to Android too, like a Samsung phone, like the top ones, right? Top of the line Android phone is really good. So you can have things like GoPro, right? This is like a legit computer, but it's pre-programmed. It's pre-programmed to do certain tasks. This one would be programmed to basically process the images that you take, right, or the video, and you don't have an interface to connect to the wireless or Bluetooth, so they can download and upload your crazy video of you trying to like skydive or something, and hopefully you don't like do too weird things with it, right? Don't go too crazy on like activities. Anyway, so these are computers you're gonna see nowadays, and this is so much different from 10 years ago, right? No, 10 years ago you have iPhone. Sorry, I'm old. 20 years ago, 20 years ago is only just a bunch of desktop. You'd see that big monitor, right, with the big desktop and mostly mechanical keyboard. I don't know why they eliminate that like part. But thing evolve. Why do things evolve? Because we want to keep pushing the performance and power efficiency. This is one key thing that a lot of computer scientists forgot: power efficiency. you don't want to you don't want to power your computer using a nuclear reactor. Anyone here remember the day when CPU was like Pentium 1, Pentium 2, Pentium 3, Pentium 4? Like one single core, everything is about like gigahertz and megahertz.
Was that around the time with Windows XP?
Yeah. So I can tell you a story. Intel was like fabricating chips, coming up with cool design to improve single core performance, right? Coming up with giant CPU that is fast. They keep clocking them 4 gigahertz or whatever. Pentium 4 comes in, and at some point, Intel realized that, hey, this thing draws so much power. And if you plot the power, it actually go exponentially up to the point that in the next like 10 years, they need the nuclear reactor for this thing. So they say, hey, this is not fly. This is not gonna fly. And that kind of spawned the concept of multi-core, right? Why? Because when you run the computer, you don't just run one program. If you have single core, they only run one thing at a time. Say you boot up Microsoft Windows, right? Inside Windows, use Microsoft Word. Those are two different programs. The way single core works is they will run Windows, kick it out, run Microsoft Word, kick it out, run Windows again, right? Over and over and over and over again. And you learn how to do this in a really, really, really miniature amount of time in the OS class. But the key thing here is why don't you just have two copies of the same core? It's a lot more scalable, right? So that's why you have dual core, then a quad core. And this way you have like 8 cores machines, 48 core machines in server because of power efficiency. In IoT devices, how many of you imagine IoT devices that is connected to, say, a solar panel or a battery? It's everywhere, right? So power can get interrupt. It will be gone for a little bit. So you need to make sure your program doesn't draw all the power in the battery and die. You don't want the computer to die. There's also like another side research that go into like, well, can you resume your program when the power goes off, right? It's called intermittent computing. I'm not gonna talk about that, but if you're interested, definitely let me know. It's a really, really cool like architectural topic on like how to actually enable this. Uh, and and so basically power efficiency is important. You want to make sure your phone here stay alive for a day. This thing is a little bit too old, so my battery is bad. Uh, I think this thing only lasts about like 6 hours rather than 24 hours. But my wife, like iPhone 12 Max Pro, lasts about 2 days. And I can tell you this story. When I was at NVIDIA as an intern, right? Uh, one of the things that they have to do is they'll know that this is our power budget. It cannot go beyond this many watts. Every single thing you design will never in total exceed that watts. It can be 100 watts, 15 watts, 20 watts, 200 watts. It kind of put the roof on how much performance you can get. It put the roof on how much inefficiency in terms of power you can get out of the program and the driver and everything, right? So these are new considerations. And a lot of the time when you program, we abstract the heck out of the hardware. You never realize that there's an actual computer running your program, right? So you use a lot of abstraction that leads to more productivity because it makes sense. An average, I would say, like if you get employed, let's say you finish PhD, because I know the number roughly, right? If you get a PhD and go to Google in California, you get paid about like 200K per year. That's like a starting salary. That's a lot, right? It's a lot of money. So I think a master degree or undergrad is like 100K to 120K, 150K. And then you'll get, when you get promoted, you're going to reach that point too, right? So people cost money. The way program should be designed, like the programming language, these days, there's also the consideration on how easy it is to program so that we don't waste human time. Everything should be automated and hopefully optimized, but you protect the programmer from like thinking about too much of the detail, right? And that's important. You want to make sure you don't like ended up getting bankrupt because you would have to hire like tons of programmer. What you might not know is like when you have this abstraction is what instruction are actually executed, right? When you call a function, is it an add, multiply, followed by compare, if else, right? What if you run the same code on a different machine? The abstraction is helping you to run the same code on a different machine. But if it doesn't work, you need to be able to fix it, right? So hopefully, if you get to know more and more about the lower level languages like C, it helps you tackling those problems, right? There's a distinct amount of abstraction when you compare Python to Java to C++. Anyone here tried to play around with assembly before? I just want to like see if you feel the pain of like programming assembly versus programming in Python.
Uh,
Don't worry, you get to do that. I'm joking.
I did ladders before.
Oh, okay. Good, good, good. So is it painful?
It's yeah the P is the program for PLC. Yeah,
It's like it's limit. There's a lot of limitation, right? When you deal with this like close to hardware program,
yeah.
and a lot of things like Python, Java. There's like a lot of awesome folks in programming language and compiler. Also theory folks like Ajahn Kanat who kind of like together helped improving programmability, right? To make it easier to program. But at the end of the day, the reason why we force feed you C is so that if it comes to the day when you need to look at this code, you know how to fix it. Uh, and you probably don't want to like go to the machine code or like control each transistor individually. But imagine this actually how computer actually function. So having the knowledge of like lower level program allows you to think a little bit more about, okay, when I write the code, this thing happen, right? So now that I say that, hey, you really don't need like machine level knowledge. Why should you care, right? So the reason why you should care is what if your code is slow? Your code consumes too much energy. This is important. Like, let's say you write a Python code and you didn't realize it because you are working in machine learning. You only care about the accuracy and like whatnot, right? And then you launch the training process. You go away for like 5 days, come back. It's not done. Have you ever wondered like, can I do better? Can I actually make it faster? A lot of pitfall in like these machine learning research are like they never care about performance, and it's not true. Some groups do care about performance, but it's as I feel personally, it's not enough. Like you should care about energy efficiency and performance a little bit more to make it useful. You switch to a better computer, but somehow your program runs slower, or you switch to a better OS and somehow your phone is slower. Like how many of you upgrade your iPhone and it turns out your iPhone is a lot slower? It happened to me. I'm sure it happened to most people, right? So that's the reason why things are faster, why things are slower. That's a design trade-off. I'm not saying it's bad or good. It's a design trade-off. A lot of things you do in computer science and computer engineering, that's not like quote unquote perfect solution, but you deliver the correct trade-off. uh, Programs sometimes produce incorrect results, right? And you want to be able to debug them, and hopefully you have tools to help for the debugging process. You run into system level bugs. You see error code that's like, I don't know what's going on, right? Your code may computer hangs. This can happen too. You want to know low-level programming a bit sometimes, because when you try to trace through what happened with your code, you might stumble upon like some open source library that you use that are written in C, and it's got hang like it gets stuck over there. So you want to be able to like understand what's going on. Your code can shut down a computer. It can happen. Like basically, sometimes if you use too much resource, thing will reboot, right? You'll run out of memory, or some. If you hack kernel and kernel broke, it will shut down because it doesn't know what to do. Right? So knowing how computer really works help in all these cases. Uh, so here's the computing stack, right? So a lot of classes you'd learn here would be around these three blue block boxes here. You look at a problem, you come up with an algorithm, and you solve it by writing programs. If you think about it, there's so many things going on underneath that you can also contribute to, right? You can design a better compiler to make your program magically faster, right? Without changing your code, right? You can design a new language that you can change the code in a way that's easier to understand from the hardware so that it's faster. You can look at the runtime system and operating system to make sure things run really well, right? How many of you heard about container? Docker? Yeah, Docker is one of the container software. What it does is it's kind of like virtual machine we've been using, but the difference that I'm gonna it's a high level of difference. Like there's so many other differences between VM and Docker. But one of the main differences is Docker would share the same operating systems, right? But then even with that, there's somewhat like overhead when you run these Docker instances, right? You will then realize it's actually slower than running your program on a machine without the Docker. Similar to virtual machine, when you run things on a virtual machine, it's slow. It's really slow. There's actually a lot of system-related reasons and system-related research that go into how to make this faster, right? Because that's the benefit in using Docker. It's a lot of benefit. You can look into ISA. How many of you heard about this Apple M1 chip? The new MacBook that come with an ARM chip. So if you look at the last product launch for MacBook, they actually create their own chip for their MacBook, and this is powered by an ARM chip. An ARM chip, basically ARM is an ISA. It's different from Intel x86 ISA. Actually, x86 ISA that you use nowadays is actually owned by AMD. There's like a historical stuff that happened. I was about to say the S word. A historical sequence of events that happened, and Intel and AMD were competing on who get to use the ISA for the 64-bit machine, right? And AMD came out on top. So the one you use nowadays, AMD 64. So those are the ISA, and the ARM ISA and the x86 ISA offer different things. It actually offers different instructions. Each instruction will govern what goes into the hardware, right? So it does offer some trade-off, and somehow the M1 chip is really power efficient. You can kind of like have your laptop staying on for days. And I'm like, whoa, that's good. You can do what I do. Microarchitecture, I design hardware. So I literally go and like say run program, try to analyze bottlenecks and make a better hardware so that your computer is faster, right? And these are things that are going on inside the computing stack. If you go toward like electrical engineer, then it becomes like circuit, device, electronic, and at some point you appear in the material science region where you come up with new material. So hardware person like me, somehow I look at like, okay, this new material sounds cool. How do I run a computer on it, right? That's also like a lot of new memory that comes out that would be a lot bigger and hopefully not slower, right? And these things can be exciting. So most of the class here you focus it at the MUIC degree will be on these three things. This class will touch like kind of like the interface between these like 5 stacks. And most of the time you need the language C for that. Why is that? It's kind of closer to this lower level of the stack, so you can program your computer based on what you write in C code. What system and architecture people do would be basically links the gate and wires, right, into computer codes and make it run. So everything, one big thing before I move on to C is everything eventually becomes the data, right? When we're learning Linux, we said everything is a file. What are files? Files are data. It's 1 and 0. It's a series of 1 and 0 that somehow denote that. That's a file. That's a program. That's a file. That's a file that represents executable, right? It's just 1 and 0. When you run these programs, they're stored in the main memory, in your actual DRAM, right? The CPU then access the program and the data from the main memory. So let's say I want to run this program. I initialize I to 10, J to 20, and I just do I plus J, right? In here, you start with the program, right? Then it gets compiled to binary. So the binary will like doing the add and write the result back to K. The runtime system launch the program. The OS come in and say, hey, okay, the user say run this program. I'm gonna look at the queue and see who get to use the CPU. They pick it up, run the program. ISA govern the fact that it's kind of like a cheat sheet for the hardware to say, if you see this pattern, it means an add. If you see this binary pattern, it means store this data at this place. So that's what the ISA is designed for. It's just a cheat sheet for the hardware to know what to do with the binary. Microarchitecture is where you implement the adder and multiplier and work with the ISA to do that exact same line, just adding the two numbers together, right? So here is a high level example. Let's say you have a program, right? The first thing you do is compile, like compile the program into binary. A binary file is just executable files. It's still a file on your hard drive, right? Over here, you have your memory, which we would use right now, DRAM, right? This is what, whenever we say memory in like a product or something, it means DRAM. This is the area where if you want to run the program, this binary will be stored here. And let's say you want to run the program on another piece of data. So the data will be stored here, right? And if you look at your CPU, so I'm going to use a different color again, right? Your CPU. From the CPU point of view, right? It has a direct interface to the DRAM. There's a direct interface where CPU can say, hey, go look at this line. Look at this line. Get that line. So this line will be transferred over to the CPU, and CPU will be like, okay, I see 10101111. What does it mean? The ISA would come in, translate this to maybe it's an add value A to value B and write it to C. So you want to add these two things together and write it to here. Once you run it, say you run this line, the result is C will be equal to A plus B. This is a super high level. There's so much actual fine detail going into this process, right? But hopefully you get a big picture, like a really, really, really big picture on when you run a program, what really happened. you first compile the program int ij, right? And then k equal I plus j. You compile, it becomes just a bunch of binary. This binary get copied over to here to the main memory. It's just a bunch of 1 and 0. CPU read those lines and look at this. Okay, I see this a bunch of 1 and 0. Tell ISA, please tell me what does it mean. ISA will tell, okay, it means you are doing this add. Let's do an add. Run, commit the result back, write the result back so that the user see the result of your program. Any question before we move on to C code? All right, so now that we hopefully, if you have any follow-up question, please do let me know. What I've been talking about in the last 40 minutes is not actually intended originally for this class, but I added anyway for all the class I'm teaching for system skill because I feel like to know how computer work before you dive into C code, you should know how roughly like what happened when you run a program, right? So let's start to dive into the concept of C, right? Why C? The first thing is like, why should I care about C? Hopefully you buy it at the first bullet point. It's really fast, right? How many people want to write or let's say you download a program, right? Or games. How many people want that program or games to be faster than before or after the update, right? You want them to be fast. You want to be honest, in a magical world, every program should be instantaneous. You run, you got the result right away, right? So C is a good bridge between getting a really fast program. You have a direct control, right? You have a direct control over memory location. This is a big difference between C and for those who take OPL, the parallel programming class, somehow you take that class before this class, and I know one of you for sure did that. This is a big difference between C and Rust, right? Rust doesn't really allow you to control memory location. C does. That's the trade-off. Rust is a lot less error prone because they don't expose that interface to you. In C, there can be a lot of bugs that come with this, but it makes programming devices a lot easier. A lot easier. Let's say you have to do embedded system or IoT in a small devices. Using C is your bread and butter because you can point to the exact location in DRAM, say, write that data over there because someone else will read it or something like that. It's minimal, it's clean. So if any one of you are like minimalist, I guess you can use C. It is really can be minimal. I'm not really totally by the word clean. It can be hectic as well, depending on what type of programmer you are. But you can make it really clean. It's compact. A good thing about compact code is it's good for embedded processor. Why? Let's say you want to program a small sensor. A sensor is about let's say the sensor is about like 2 centimeter by 2 centimeter big, right? It's so small. Will you be able to get a lot of memory out of that sensor? No. But you remember, right? Your program, whenever you run the program, both the program and the data has to be on the memory, right? It has to both be on there. If you write code in C, this part would be small.
Is
It'll be
this the
small.
is the word modular?
Modular is a little bit different, I think. Modular also like refer to the fact that you can kind of like move this around, I think. And kind of like take one course out, bring another modules in and things like that, right? So this is basically just short assembly. When you compile code in C, the code in assembly can be really short.
Oh,
Why is that the case? Because you don't have those abstraction. So Java and Python is likely to end up with more assembly lines,
Oh,
right? Because you need to kind of support those abstraction. Without that abstraction, you are basically free for all. Good luck with the code, but I mean, if you know what you're doing, it can be really short. If you don't know what you're doing, it can be amazingly long, right? So it depends on how good of a system programmer you are on the side of like optimizing the code size, optimizing the code size. Uh, if I'm not sure how many of you are in this like computer Olympic team for Thailand, right? But say during the Ajahn Kanat year, or like I guess the end of like mine age group, I guess. Code size is a big thing because the when we program, some a lot of time we program in this IDE called Turbo C. It's really old and you don't have a lot of memory. Like your program has to be compact, otherwise it won't run well. Okay, so back in the day, you don't have more than say 2 MB of memory. Imagine that. And it can be realistic in embedded devices that are small, like a sensor or just like a switch or thermostats, right? So you want to make sure your code fit in there because you want to make sure they can do something useful with it, right? Why not C? Is that a big question because I don't want to tell everyone say "Hey, always use C as a language. My motto of what language to use the one that makes sense. It's like when you go eat, right? You have chopsticks, you have fork and spoon, you have your hands, right? You pick the tools that match the thing you want to do. If you want to eat noodles, probably chopstick and spoon. If you want to eat like a soup and rice, a spoon, right? Uh, don't. Or if you want to eat like sticky rice, use your hands. It's fine. Pick the tools that is the most efficient, right? You need to manually if you don't want to like some type of program requires a lot of like thought on the algorithm side, and you don't have to worry about where the memory would go. Use Java, use Python, use Rust. It's just totally okay. If you don't want to interface with the computer systems, it's totally okay to use higher level language or even C++. C++ is really powerful because it offers the speed of C and object-oriented programming. And there's already an email asking me, and it's a really awesome question, right? On why do we start with C rather than C++? Uh, the answer that I would give is because C offers the interface between you and the system, right? You can do a lot of this like memory management. That's already enough potential bugs that you can run into. So I don't want to tie in object-oriented programming so that your life will be miserable when you need to write your assignment. If you want to learn C++, imagine basically C fused with Java, the object-oriented programming of Java. And these days they also support like Lambda function. It's so many additional support that C++ provide that it doesn't really fit in the theme of like learning how to work with the system, the computer system. So C is a little bit better for the class setting. It's not object oriented. So if you want object oriented programming that's too fast, I definitely encourage everyone to use C++ if that's the case. And I do too. I use a lot of C++. And it's not, if you learn how to use C, knowing how to use C++ is not hard at all. If you know both C and Java, it's almost like, okay, it's kind of the same concept. You just need to know the syntax. Uh, there are many ways to create bugs. By the end of this class, you know what I mean. Um, and you don't have to be that creative to create these bugs. Also by the end of the class, you know what I mean. I think that's self-explanatory, and I think the best way to experience this is to experience using your own like hands-on experience in a bit. Uh, all right. So let's start with C. How do you create a function? Right? This is kind of like the bread and butter of programming. So it's similar to Java. Each function has a return value. Input to a function has a type, integer, character. Uh, it can be a complex type like struct. We will talk about struct in a bit. I think the next lecture. This is an example. These functions are physically located in memory, as I said, right? And this is one example. In add A and B, return A plus B, right? What does it do? Take A, take B, add them, return. Any questions on this? So make sure the return type match with what you declare. So this is the return type. And these are the input type. So this is one of the common error that I see from the previous instance of this class whenever I do office hour or like this programming after we are done with the lecture, is the wrong type. And the compiler would basically yell at you is type mismatch, and every student will be like, what does it mean? Well, you put in the wrong type. Just make sure it's the same type and you'll be fine. This can be a little bit confusing when we start talking about pointers, which we'll cover on, I believe, Thursday. And that's where most of the error comes from. Right? And then there's a main function. The main function is when you run the program, this is the function that get run. So after you compile the C program, it will first execute these line, whatever line is here, whatever you write here, that's the first line of the program. There are C support multiple data type, like other languages. You can have integer, character, float, double. These data, the data type represent the value. For example, if you say int a equals 65, and you say print in C, you call printf, print function. In here, %d means you want to print a number, and a, %c, you want to print a character representation of a, you would then get the letter big, the capital A. Okay. The data inside these variable literally are binary, and if we interpret on the as like certain type based on what you tell them to do. And it only support basic data type. You can't you can define your own complex data type, but you need to manually define that. And there's no boolean. No boolean. If you want a false, 0, true, non-zero, right? True is non-zero. So one of the common mistakes, second common mistake that I see, if you write this means that I'm gonna first assign the value of A to be B, because it should be equal. If you have that typo, it will be, I'm gonna assign the value of B to A. If there's no error, it's fine. It will return no error. No error means if I remember correctly, this would return the value of B, which means somehow it's always true. Right? So this is like potential bugs that you can have. And somehow I make these mistakes too. When I'm like programming at 2 a.m. at night, I miss one equal sign. It threw me off. Right? So this is something that you should be aware of. Variables, you can declare them similar to Java. Nothing much here that I need to explain, I believe. You can work with variable the same way. You can assign value from one data size to another, right? Let's say B, right now B is an integer. You say long D, right? A long integer is bigger than an integer, but you can say D equals B, and that's fine. And that's fine. We will talk about conversion, where you can convert data type by actually casting int right? Int in parentheses a, it means that I'm gonna represent that variable as an integer. So be careful when you convert data type of one type to another, right? Let's say int a is 12, b is 5, and you do a divided by b. If you do a divided by b, this is basically 2. Because it's an integer. Integer divided integer should get an integer, so it's not 2.4. 2.4 when it gets cast to integer is 2. If you want 2.4, you need to do float a, make a becomes a floating point, make b becomes a floating point, so it becomes 12.0 over 5.0, which is 2.4. So be careful with that because this can lead to bugs. This conversion thing so I think there was like a big accident that happened with like one of the rocket launch back in the day, right? That come from like this conversion. You do a conversion by mistakes and it turns into like a negative value, so things blew off. Uh, okay. Yes. So that's a great question. So the question was like, can I go over the size, the data size, such as the size of int, the size of character. So character usually is 1 byte to 0 to 255. Integer typically is 4 bytes, but in some version of GCC, the C compiler, this can be 8 bytes. So integer is a little bit that off thing that you can have different size. The best way you can tell is called this function. There's a function called size of, and you put in the variable. You can even put in just the word int. Size of int will print the number that represent how many bytes does this cost. So hopefully that answered the question. And the reason why I don't want to give you the specific number is because if you Google different version of GCC, they will give you different size. But character is 1 byte for sure. Long integer is typically 8 bytes. Integer is 4. Short integer is 2, but it kind of depends on the version. All right. So for operators, similar to Java, you can do a plus b, b plus plus. Not sure what else I can say here. It's pretty self-explanatory. As I said, A equal B and A equal B are different. So A equal B means I'm going to assign the value B to A, then return B as a result. You can do logical operator. The exclamation mark is a logical not. If it's true, it's flipped to false. If it's false, it's flipped to true, right? And when false, which is 0, so false is 0, right? 0. So if you say not 0, this is 1. So if you want to somehow do the conversion from non-zero integer, right? Non-zero integer. So let's say it's 31. You want to convert to 1. What you can do is to do this. Not 31. Because not 31 will convert 31 to 0 because you need to force them to be false, right? 31 is true. Not again will flip from 0 to 1. This is different from negate 31. This is basically 31. You flip the bit and flip it back. How does logical work if there's no Boolean? So Boolean is treated this way. 0 is false. Everything else is true. Everything else is true. Bitwise operator, as I said, perform the actual bit flip or bit operation, right? This is bitwise not and or XOR, right shift, left shift. So let's say I have the number 31 again, right? What is 31? 1, 2, 4, 8, 16. So that's 31. And let's say it's just a character, so it's only 1 byte. It's a character, 1 byte character. So this is 31. If I do not 31, this is basically I flip out the bit. It will become 111000000. What is this value? It's not zero. It's not zero. We will learn what this value is in the next lecture when we talk about data. Yes. So this is basically 224. If this is unsigned, if this is a signed character, then it's negative 128. So this is basically negative 128 plus 64 plus 32. If you not 31, you flip all the bit back, so you get 0, 0, 0, 1, 1, 1, 1, 1 again. Right? This is different from negate 31. Negate 31 literally make this 0 because you want to not the Boolean version of that. This is 0 because 31 is true, not 31 is false. The only value that represents false is 0. Not 0 is 1. Not 0 is 1. Okay. Is this clear? If it's confusing, let me know, please. If it's still confusing after the class, definitely check back with me. I will be more than happy to make sure this is not confusing. Because this is a pretty big component when you need to program in embedded systems, to be honest. You somehow need to, in a lot of cases, you somehow need to do the AND and OR and bitwise operation as well. You can do / for comment. You can do /star if you want to comment like a big block of comments. Sorry. So that's it for putting in comments. You can have control structure, if, and else, or switch case, which look like this, right? Self-explanatory, pretty much the same as Java and almost the same as Python, but you need this bracket rather than indentation where you have to put tab, right? The tab thing in Python is weird and I never got used to it. But barring that, everything else Python is awesome. You can do a loop for I equals 0. So this means that I'm going to initialize I to 0. So that's before I enter the loop. Then I'm going to check if this is true. If this is true, do something in the loop. If this is false, exit the loop, right? And then after this is done, do whatever you put in here. So this is initialization. This is done done at the every end of the loop in each iteration. All right. It also works with while, and then some statement. Do while also works in C. You can use break. When you put in the keyword break, it kicks you out of the loop. Basically, exit the loop. You can use continue. The difference between break and continue is continue skip only that one iteration and go next to the next iteration. You can print like hello world. You can scan where you take input from the keyboard, right? From the standard input using scanf. I'm gonna post the slides, so don't worry about that. You can compile and run your code. You can use the GCC command. Mac user use dlang instead of GCC. But make sure you double check with the GCC version in our SysQ server because that's where I'm gonna compile your code on. I don't want to run into the case that you have a perfect code that run in Mac and I don't have enough money to buy a MacBook. That I cannot grade your homework. Right? Make sure it run on a server. And I'm joking, but I don't have a MacBook around me that I can just test your code. So please, when you submit the code, check if it compile using GCC. And you can run it by doing this. GCC, your C code, dash O mean I'm gonna create an output executable over here, right? I'm gonna show you an example in a bit, but before we end the class, end the lecture, I'm gonna go through an actual example. Here are some additional references. There's a C manual for the GNU C. There's also C standard library that you can check out. There are a bunch of things that you can do. There's a format string where you can, when you want to print certain things, you can go to that link. And before we leave today, I'm going to do 2 sample code, right? The first one is a basic hello world. The second one is a Fibonacci. I'm going to do 2 versions, a loop and a recursion. So before I begin, let me just connect to the SysQ server. And in the meantime, if you have questions, feel free to ask me. All right. Oh my God, my eye is so bad and the font is so small that I can barely see that as well. So let me increase the font size. Now I understand all my professor jokes about their age, and now I feel it. Okay, so let me increase the font size real quick. Change to, let's do 20 and bold so that I can clearly see the text. Yay, magic. All right, so let me make a directory for, I guess, lecture 5 test code. Right, and let me go in there. Okay, you see the screen?
Yes, teacher.
All right, so let me do the hello world first. So I'm just gonna create a file called hello.c. The first thing I need to do, because I want to print out hello, like hello world, right? So I need to include what we call a standard library, stdlib. This allows me to print things. Basically, you put in pound sign include. Pound sign include basically mean include whatever is in this standard library.h. .h. Standard library.h has the definition of how you can run printf and scanf. And as I said, the main function is called itMain, right? And because I want to make sure I can return the correct execution, I'll just say return 0, right? So what can I do? I call printf hello class, right? Okay, and I can save the file, right? So what would this do? Just print hello class. So if I want to actually compile the program, because right now it's just a C file where computer doesn't understand this yet. If you want to make sure a computer can run this, you can say hello.c-o, hello.o. All right. Oops, my bad. It's not standard library, it's standard IO. Standard IO, not standard library. Standard library are things like power function or things like that. So this is what the compiler would tell you. Hey, I don't know what printf is doing, so you better include standard IO.h. So now it stopped yelling at me. And if you want to run it, as I said, you need to do // right? And as you can see, that's hello class. You see hello class get printed out, right? One quick thing is I didn't actually put in a new line, right? So that if I want to put in a new line so that hello class is like its own one line, I can fix my code by going back to hello.c, right? And then if you go to format string, one of the string you can put in is new line, which is \n. When you run the same, well, I first need to compile the code again. And when you run this code, now you see hello class with a separate line. Right. So I definitely recommend you to do the same steps at some point to make sure you can run the program on a server. Because Hello World is like the most basic program. You just need to compile given the same command as what I showed earlier. Uh, Let me now do Fibonacci. Let's see, right? Again, I'm gonna include standard IO int main, right? And again, I'm gonna return 0. I'm gonna do Fibonacci using different version of Fibonacci. The first one is the most obvious one, which I'm gonna call the recursion Fibonacci, right? So I say recursion fib of n. I'm gonna first declare int n, right, and say n equal, let's say 10, right? I do %d, and I want to have a new line to make sure it's clearly the formatting is nice, and then I print fib recursion of n. Let me close this part so it doesn't block my view. All right, now that I declare this function, what I need to do is, well, first of all, I need to return something, right? And I'm going to create a function called fib recursion. What does it take? It take n, right? What's the type of n? What's the data type of n?
Integer.
Yes, so you say integer, and it doesn't have to be the same name. I can say A, B, C, D. Well, it's too long. Just say A, B, C. I don't want to type a lot of A, B, C, D. Let's make it cleaner so that you can read the code again. Let's say input. I want to do a recursion where of the input. How do I write Fibonacci using recursion? Is this covered in the Python class or like the first class? So here's what Fibonacci is doing, right? So let me make a comment here. So this is comment. Fib of n equal to fib of n minus 1 plus fib of n minus 2. And if n equal 1, 0, fib of n equal 0. If n equal 1, fib of n equal 1, else so that's kind of like a pseudocode for Fibonacci, right? If n is 0, fib of 0 is 0. Fib of 1 is 1. Otherwise, fib of n is fib of n minus 1 plus fib of n minus 2. Minus 2. So how do I write this? Well, obviously, the first thing is I need to check if input is, well, is less than 0. What do you do? This should never happen. So you can say printf, what the heck? Else, if input is 0, what do you do here? What do you return? What is fib of 0?
0.
Yeah, so you return 0. Else, if input equals 1, what do you return? 1, right? Else, return what? You want to call fib of n minus 1, right? So it's fib recursion of n input minus 1, right? Your input is a variable, plus fib recursion of input minus 2. And that's it. That's the code. And if I run this, So let me. Oh, that's not an O, that's a 0, my bad. Okay, so it's yelling at me. Something is wrong with my code. What does it say? Expected and a bracket before else. So let's go back to our code and see what's wrong with it. So this is basically, I'm going through my own error to make sure that if you see some of this error code, you can hopefully check what it means. The first time is like, I don't know what -0 is because by my own stupidity, I type in -0 instead of -o. The second time I type -o, it say, okay, I on line 15, right? You see 15:2 over here. 15:2 means this is line 15. So let me go to line 15. What is that line? This line here, right? You see my mistake. I have open bracket. I forgot to close it. So I can close it here. One quick note, if the code after the if else is only one line, you don't need a bracket. So I can delete this whole bracket as well. But since it's complaining, I will just fix it. And here is the correct thing. Right, so I can run fib.o and recursion of fib of 10 hopefully is 55. Can someone check? Sorry. Is that 55? Let's do another approach, right? So let's go back to fib of C again. And I want to do solve Fibonacci using a loop, right? So that I can show you how loop works. Right. The way you can do Fibonacci using a loop is, let's say, okay, I forgot that you need the concept of an array. How many of you here don't know what is an array? So everyone here knows what's an array. Okay. If you don't know, yell now because I can implement without an array as well.
Was array and list?
Wait, you do know or you do not know?
I'm asking because I kind of forgot.
Okay, so we'll cover array in a bit. So let me implement without an array. All right, we'll cover array next lecture. Let me implement without an array. So basically, if you look at Fibonacci code, what you can do is basically you can start with 1, right? So let me put in the comments, right? Fibonacci is basically you start with 1, right? So fib of 1 is 1. Fib of 2 is 0 plus 1, which is 1. What's the next number? Fib of 3 is fib of 2 plus fib of 1. So it's 1 plus 1, which is 2, right? Fib of 4 is 2 plus 1, which is 3. Fib of 5 is you add these two earlier number together. That's 5, right? Fib of 6 is you add 5 and 3, you get 8. Fib of 7, you add 8 and 5, you get 13. Fib of 1, 2, 3, 4, 5, 6, 7. So fib of 8, you add 8 and 13, you get 21. Fib of 9, you add the earlier two number, you get 34. And fib of 10, which is correct, so you get 55, right? Fib of 11, you will then get 89. You basically add the earlier two number you've seen, right? So can we imitate this algorithm that I just explained it to you? I'm going to loop around, and the first time I'm going to start with 1. The second time is 1. Otherwise, I'm going to add the earlier two number together. So start with int number 1, I guess, num2, and then result, right? 4, int I equals 0. I would just put I here because C is an old language. If I do for int I equals 0, I'm pretty sure it will complain. So I need to start with initializing, declaring an array I. And now my session hangs. Yay. Okay, so let me reconnect. Yep, it does hang. So let me reconnect. I'm sorry. Close the session. $20 bold. No, not italic bold. Yay. Okay, big font. I can see again. Okay. Oh, what was the photo name? Lecture 5 test code, right? So we were at fifth C. And this is what happened when you use Vim. You recover. All right, so that's where we left off. We started for in I equal, right? And that's when my thing tanked. So from I equals 0, I is less than input, I plus plus. And please fact check me if I'm doing wrong things here because I am tired. So if I equals 0, if I equals 0, what do I return? My bad. If I is equal 0, I will do nothing because the first iteration. No, the first iteration when I is 0 is fib of 1. It's fib of 1. So this is, I would just say num1 equal 1. This is not efficient at all, but just to make sure it's clear for you guys, basically, if input is 1, you want to make sure you return 1. So you want to make sure the result is actually at least 1, has the value 1. Then you return results. Right? If I is 1, you see one of my mistakes here. It should be equal, right? If I is 1, so that's fifth of 2. Fifth of 2 is what? Fifth of 2 is 1, right? So result is still 1. Otherwise, for any iteration after the second initial value, which is 1 and 1, the next thing we need to do is result equal num1 plus num2, right? You want to just add the earlier two number together. Then you update them. Let's just assume num1 is let me recall this. Num older, num newer, right? So you just say num older will be the older of the two number. And num newer is the newer of the two number. Over here, you add the older number with the newer number. And everything I do here is on the fly, so if that is bugs, let me know. And then, what do? The older number should now take the newer number, right? Then, newer should be the results because the next iteration, you're gonna add older and newer again. Basically, you move everything in the windows, blah, 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 blah. So let's assume this is correct. I don't know why I typed that word. So this is the loop. implementation of fifth of n is fifth loop of n, right? And hopefully this works. So let's try this. GCC, right? Line 30, I forgot something. Line 55, I forgot something. And line 62, I've also forgot something. So let me check that. Oh. So what is line 30? Here. Oh, okay. I accidentally have semicolon, which means I'm gonna finish the function. That's not the case. I want to actually expand the function. So that's the first error. And I fix it, so it should be gone. Now it's line 55. What's wrong with line 55 here? By accident, I don't know why that text appears, so let me delete it. And then the rest is line 58 and 50. Why are there so many random texts? Oh, SDF. Oh, I was trying to like check whether the connection is there. I'm sure that's why it's bad. Okay, now everything works. And if I run Fibonacci again, I should see the same number. Yep. So it's the same as, yeah, exactly. So I just saw the text on the chat here because I was looking at my monitor. I'm so sorry. But yes, it's the same as using the list. If you want to use an array, if you want to just implement, basically your answer is correct. It's the same as I is equals 0. So just to make sure these two functions are the same. One other thing that are different is over here, I haven't really checked if input is less than 0. So I can say if input is less than 0, print f, what the heck? All right. So you can, well, first of all, you can do this. And then one more thing that you might not realize, this doesn't cover the case where input is 0. And when input is 0, it means something. So I need to make sure I cover the case when input is 0. You return 0. Fifth of 0 is 0, and that's 9, 0. Right? Now, the last thing I'm gonna show you is how to use scanf. I want to take a text. Awesome. That's a great question. Actually, now that we talk about speed. So the question is the speed of both two-way of iteration. Are they different? Yes. If the number is big enough, this loop will be better because you don't call a new function. Whenever you call a new function, something happens. And we actually learned this toward the end of this module when we got closer to assembly. There's a lot of assembly code that involved in initializing the function. There's also memory accesses that involve in initializing a function. With this loop implementation, if you learn assembly in the bit, basically, after we're done with C, we talk about assembly in a bit. You will then realize everything here can be stored in a really, really, really fast memory that's on your CPU. It's called register. Because you only involve 4 variables, I, num order, num newer, and results. So everything here can be done really quickly. So the loop implementation, in theory, should be a lot faster. I'm pretty sure if the number is big enough, it'll be faster. Can you tell the difference? I'm not sure. Computer is fast nowadays, right? So unless you type in the number in the range of like 10 millions, the difference won't be that much. It will be like maybe 2 to 3 or 4 times slower, which is a lot. Like 4 times slower is a lot, but it's between like 1 millisecond versus 4 milliseconds. You cannot tell. It's still really fast. So, but that's a great question because this is only one function call, Fibonacci, which is something super basic, right? In a real program, there's so many things involved. So that is a question that hopefully most of you will always keep that in mind. So the last thing I want to do is instead of taking the value of n to be 10, I want to do this. I want to scan the keyboard input. So I can do scan %d. I want to scan the integer that and then store that into n. So you can say this is a variable name begin with the ampersand. We will talk about why do we need ampersand in a few lectures ahead of us. But I'm not going to talk about it now. Make sure you have ampersand in front of the variable name. And you see what will happen. If you run fib.o, it will actually now wait for my input. So I can put in, say, 5, right? Now, say fib of 5 is 5. I want to put in 20. Fib of 20 is 6,000. I want to put in 100. Fib of 100, this start to take a while, right? Yeah, it's actually quite a long time. Longer than I expected. And we are still here. Interesting. This is longer than I thought. So let's do fib of 40. So you get something like 1,000,000. Fib of 50. You remember, right? We actually call the two functions back to back. So notice how the recursion stays silent, but the loop one come out right away. Right? See the difference in time. So let's do 40 again. You wait a while until the recursion come out. So you actually, once I hit enter, you actually wait a while. But for some reason, the loop implementation come out right away, right? Come out really quickly. So let's actually comment out the recursion part, right? So we just want to do the loop implementation. And we saw that with the number 50, it takes so much time, right? It takes so much time. So let's actually do 50 again, but with just the loop. It's quick. It actually overflow into a negative number, but it's really fast. You see the difference, right? You can actually now compute 100. It's quick. It's still quick. You get the result. This is actually result, but it overflow into negative number because you don't have enough binary to store this value. So let me change integer to long. Right, everything is now long. Oh, it meant. So let's do 50 again. Now still negative number. So that's too big, I guess. Oh, because I printed. So here, I want to print it as an integer, right? But this is integer. I want long integer. I want a long integer. So I need to compile first. Right. Oops. ER long. 14 and 64. So let me fix that. Oh, print. I see. Whenever I type the word print, it becomes PR long because it has the letter int. Yep. 34. And 64. Why are there so many of this? Oh. Okay, so it should be fixed now. Everything should be a long integer rather than integer, right? And we do 50. Now you get an actual positive number that correctly represent this loop implementation. 100, let's see if it's still there. Yeah, so you see the number is still there, it's still positive, it's correct. 100, it's fine, right? So let's check the performance of our recursion. Oh. So I need to print a long version of that. And 50, see, a lot slower. You see the difference in the running time, right? It's a lot slower. So hopefully that really hit the nail in the head that the two implementation is so much different in terms of running time. And this is actually better than expected. I didn't know that it would be that slow starting from fib of 50. Yeah, this is really slow. It's been like almost like half a minute versus instantaneous, right? So you can time it. So instead of scanf, right, I'll just say n is 50 and do the loop version. So 0.02 seconds, 0.02 seconds. I just time how long fib.o takes to compute fib of 50. Oh, no, my bad. This is fib of 50. Still 0.02 seconds. Actually, it's even faster. Like less than a millisecond. And let me just change this to like 42. I think should be good enough for the recursion. See, 2.5 seconds for the recursion for fib of 42. Let's do fib of 42 for the loop. What's 2.5 seconds divided by 0.002 seconds? That's about 1,000 to 1,000 times, more than 1,000 times difference, right? See, you can just do something with your code. It looks stupid. The loop implementation looks really, really stupid. Is it fast? Yes. Why? You use only 4 variables. You never touch the memory. Actually, this implementation never actually touch the main memory. If you don't go to the main memory, you save about 10x. This touch a lot of memory locations, right? So hopefully that drive the point home about the speed. All right, any questions? Let me save this code. Let me actually make a directory in the root directory in syscale called sample code. Oops, I cannot do that. I need sudo. All right, and then I'm going to copy this lecture code example to that sample code, right? So that you have an sudo. Okay, and then I'm going to chmod. You can. I'll just going to let you to read it, right? To the folder sample code. So you should be able to access. Oh. I thought this is the format. Am I wrong? I'm gonna make sure you can access it. I thought it was the format. Okay, yeah, dash capital R. That was stupid. So you can see the folder sample code where you can read on that. So you can check it out. check the code out, try it out, copy it. It's fine. It's there. You can check it out. All right. So let's come back. So actually, let me exit this and come back to our lecture slides. We have in class exercise nothing related to the things we learned here, because I want you to absorb C code a little bit more. You can play around with things, but unless we talk about arrays and structure of the data, you can do a lot more things with that. That's in class exercise 3, which is useful for assignment 1. It's on scripting. In the meantime, feel free to ask questions. And I know I went like way longer than I expected. We only have about like 10 minutes left before I need to prepare for the next section. But if you have questions, let me know. So I'll stop recording for now.